Hey guys, hoping all is well with everyone. So in this video we're going to be continuing with Module 2 today. So we're going to be looking at Module 2.1 on integer exponents. So this section really highlights and focuses on the laws and properties that exponents have and how we can use those laws and properties to simplify expressions and terms that involve exponents. Before we jump into the guided practice here, I just want to go over these 6 properties to kind of illustrate the rules that we're going to be looking at and have some ideas before we jump in, to the practice here. So number 1 here, zero exponent property. This tells us that any non-zero integer or value taken to the 0 power is always going to be equal to 1. It's really important that we represent that a is not equal to 0 because 0 to the 0 power gets really interesting. So we want to make sure that we say that for all instances where it will equal 1, a is not equal to 0. The negative exponent property tells us that anytime we have a base taken to a negative power, then we're going to, in order to make it a positive exponent, we're going to change the orientation that it's in respect to the fraction itself. So in example, if you had a to the negative 2, so let me go ahead and type that. So if you had a to the negative 2, think about any number is just itself over 1. So you're basically going to flip it, and you're going to now represent this as a positive exponent and a to the second power in the denominator. So when I say that we're going to kind of reverse the orientation or position, that's going to be kind of what I'm referring to there. Product of powers means that if we take two bases that are the same to both to exponents, when we take the product, we're going to leave the base the same, but we're going to add the exponents together. So for example, if you had a to the square, or a squared times a cubed, that's going to be a to the second times a to the third, that's going to be a to the 2 plus 3, and or a to the fifth. Quotient of powers is the same idea as product of powers, except now instead of adding them, we're going to subtract them. But another rule we have to keep in mind is that a cannot equal 0, because it is possible, if that were the case, that 0 can end up in the denominator. And again, we're kind of at that point where right now, if we try to divide by 0, it's like breaking the mathematical law. So we want to make sure we avoid that situation when we're defining these terms and laws of properties. Power product means that if there are two terms that are non-identical or identical, so to speak, that are being multiplied to an exponent, then that's going to be equal to that first term to this to the exponent times the second term to the same exponent. Power to a power means that if you have a value taken to an exponent and that term itself is taken to an exponent, then the resultant is going to be that base to the product of the two exponents. So if it was a to a squared, or a to the second, to the cube, or to the third power, it's going to be a to the 2 times 3, or a to the sixth. Okay, so let's go ahead and look at some of these here. And I did number these so I can highlight the rule that we're looking at for each of these questions in the guided practice. So for number 1, we have a to the negative 1. That's going to be rule number 2. So this is where, again, we want to illustrate this as the value itself over 1, and we want to kind of change the orientation that it's in respect to the fraction. So this is going to be 1 over 8 to the positive 1. So that's what's going to allow us to make that positive exponent. And then that's just going to be 8 to the first, which is just going to be 1 to the 1 over 8. Okay. Number 2 is the same, very similar to number 1. So this is going to be rule number 2 again. This is going to be where can be observed as just 6 to the negative 2 over 1. So we want to put the fraction in the they want to put the base with the exponent that is negative in the denominator, making it positive. So that's going to be 1 over 6 squared. And remember, anything squared is itself times itself. So it's going to be 6 times 6. It's going to be 36. Okay. Number 3 here is going to be 256 to the 0 power. This is going to be rule number 1. This is going to tell us that any non-zero value taken to a 0 power is going to be equal to 1. Number 4 here doesn't follow any certain rule that I have listed, but remember, when we represent any number taken to an exponent, that exponent tells us how many times we multiply it by itself. So we have 10 times 10, which is going to be equal to 100. Number 5 is just this kind of very equivalent to number 4, except this time it's going to be 5 times 5 times 5 times 5. Again, that exponent is going to tell us how many times we multiply that base times itself. So 5 times 5 to the 4th power is going to be 625. So 5 times 5 is 25. 25 times 5 is 125. And 125 times 5 is 625. Number 6 here is going to be 2 to the negative 5th power. That's going to be rule number 2. So again, this is going to, again, we want to represent this as, oops, that was a poor, there we go. This is going to be 2 to the negative 5th over 1. So when I mean we want to change the position, I don't mean flip the fraction. So I know, like, I'm representing these as all as over 1, and if there was something in this denominator other than 1, we would leave that in the denominator. So what I want to highlight here is we strictly just change the position of the value with the negative exponent. So the fact that all of these numerators in 1, 2, and 6 are 1, it's not because my denominator is 1, it's just because there is no other term that is other than what would be just the exponent that was negative by itself. So we're just going to be putting everything from the numerator, in this case, to the denominator. So when we put the negative 5th power to the denominator, that becomes positive, and that's going to be equal to 1 over 2 to the 5th power. 2 to the 5th power is 2 times 2 times 2 times 2 times 2, and that's going to be 32. So 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32. So that's going to follow rule number 2. So number 7 here is going to also follow rule number 2, and this is going to, again, I just want to make sure this is clear. So when we have this, all of the numerator is going to go into the denominator with these, because as of right now it's the only term or only thing that is representing the numerator. So it's not flip-flopping the fraction, it's just moving everything from the numerator, because it's the only term, into the denominator to make it a positive exponent. So this is going to be 1 over 4 to the 5th power, and 4 to the 5th power is going to be 4 times 4 times 4 times 4 times 4, which is going to be 1024. Okay. And it's going to be a very good habit to get into, especially when it comes to standardized tests. You never want a simplified expression to ever have a negative exponent. You always want to rationalize it and make it into a positive one as your final answer. Okay, so number 8 here is going to be 89 to the 0 power. That's going to be rule number 1. So anything to any non-zero value to the 0 power is just going to be 1. And then 11 to the -3 is going to be rule number 2 again. So this is going to be equal to, we want to make that -3 positive, so that's going to take, we're going to put that into the denominator, making that exponent positive. And this also is for if it was negative in the denominator. If it was -3 in the denominator, we would put it in the numerator as a positive exponent as well. So it kind of works both ways. So this is going to be equal to 1 over 11 cubed, which is 1,331. So 11 times 11 is 121, and 121 times 11 is 1,331. Okay, so that's for the first part. So far we've only looked at rules 1 and 2, but that's okay. We're going to start to look at some other ones here. So number 10 here is 4 times 4 times 4. This just represents a question of understanding that this is going to be equal to multiplying 4 by itself 3 times. This is going to be equal to 4 to the 3rd power. Now it's going to be to the positive 3rd power. Okay. This is going to be 2 times 2 times the quantity 2 times 2 times 2. This is going to be equal to 2 squared, because the first one right here is just 2 times itself, and then this one's going to be times itself twice, or it's going to be to the 3rd power. So that's going to be 2 squared times 2 cubed. We have 2 like bases that are being taken to exponents, and those bases are being multiplied. So we're going to add the exponents together. This is going to be rule number 3. Okay, so we're going to add the exponents together. This is going to be 2 to the 5th. So one way that we can visualize that is we see that there are a total of 2 being multiplied by itself 5 times. So 2 times 2 times 2 times 2 times 2. Another way that we can look at this is if we go ahead and kind of calculate this. 2 times 2 is 4, and this is multiplying. 2 times 2 times 2 is 2 cubed, which is 8, and indeed that 4 times 8 is 32. Just a kind of a way to check your answer. Now for number 12 here, we're going to be looking at a quotient with like bases. So we're going to be looking at rule number 4 here. Okay, so there's kind of 2 approaches that you can take with this one. You can take the number 4 as the quotient rule of exponents. So we have 6 to the 7th over 6 to the 5th is going to be their like bases, so we can go ahead and subtract the exponents. So it's going to be 6 to the 7th minus 5. So that's going to be 6 to the 7th, or 6 to the 7th minus 5 power, or 6 to the squared. Another way you can visualize this, if you cancel out a 6 from the numerator and the denominator as much as possible, you'll cancel out a total of 4 6s on the, 5 6s in the numerator and the denominator, and you'll see that you still have 6 squared left over. So that's a visual kind of way that you can approach this one. But we'll get 6 to the 2nd power. And again, number 13 is kind of looking at the same rule here. This is going to be rule number 4. So it's a quotient. So because it's a quotient with 2 like bases taken to exponents, we're going to subtract that first exponent from the second, That's very important. Actually, I do want to highlight that. So when you subtract the exponents, it's always numerator minus denominator. Yes, you will sometimes end up with negative exponents, and that's why we want to definitely understand the rule number 2 about negative exponents and how we can rationalize them to make them positive. Because sometimes you will have a difference in a quotient of exponents where you will end up with a smaller exponent than in the numerator than the denominator, and that's okay. And then this is going to be equal to 8 to the third power. So this would be just like number 12 if you were to list the 12 8s being multiplied here, the 9 8s multiplied here. If you canceled out all of the 8s possible to where a denominator or numerator didn't have any, you'd see the denominator would run out first, and you would have 3 8s being multiplied by themselves in the numerator. So that'd be 8 to the third power. Okay, so let's look at number 14 here. So this is 5 to the 10 times 5 times 5. Now, one thing I want to illustrate here is if you're dealing with exponents and you see that they're like bases, one thing that you can do is you can, if you don't see a base taken to an exponent, you can infer that it's taken to the first power. And that's kind of helpful here because it allows us to, this is going to be a product of powers in a way. So we're going to add these exponents together. So this is going to be like rule number 3 here. So 5 to the 10th times 5 to the 1 times 5 to the 1 is going to be equal to 5 to the 10 plus 1 plus 1. And that's going to give us 5 to the 12th power. Okay, so again, if you were to do kind of like number 6 here, but instead as a quotient, you were just going to list out all of the 5s, you would see that there are 12 5s being multiplied by each other. Okay, and then number 15 here is going to be rule number 3. So we have rule number 3 here. So this is going to be a product of powers. So what we'll do is we have like bases, both taken to exponents, so we're going to add those exponents together. We're going to keep the same base. So that's one thing that's also really important. We never want to change the base with these laws of exponents here. So this is going to be 7 to the 8 plus 5 power, which is going to be 7 to the 13th power. Okay. This 16 to, or 6 to the 6 squared to the 4th power is going to be an example of rule number 6. This is taking a power to a power. So this is going to be the product of these two exponents. So this is going to be 6 squared times 6 to the 2 times 4, which is going to be equal to 6 to the 8th power. Okay. This last rule is going to be rule number 5. This is going to be a power of a product. So we see that both terms here are going to be each individually taken to the 3rd power. So this is going to be equal to 8 cubed times 12 cubed. Okay, so if we were to take the what would happen either way is if we did 8 times 12, which is 96, to the 3rd power, that would equal 8 cubed times 12 cubed. Okay, and I think it's about 844,000 plus some more. So, but just to give you the idea that 8 times 12 to the 3rd is going to be directly equivalent to 96 to the cube. But just so we can see that property at work here. So this wants you to simplify the expression. Okay, so what we're going to do here is we are going to take number 18 here. So number 18 is going to be a rule number 5. So it's going to be, it's just a power of, rule number 3. Just to revisit number 3 here, it's going to be a product of powers. So it's going to be rule number 3. So we're going to add these exponents together. So I'm going to illustrate this as 6 to the 9 plus 0 plus negative 10. I want to be careful with our negatives here. So 9 plus 0 is 0, or 9 plus 0 is 9, plus negative 10 is equal to negative 1. So this is going to be 6 to the negative 1, which is going to be equal to 1 over 6 to the first power, or 1/6. Now this also uses rule number 2, which is about negative exponents. But we saw that as we simplified it toward the end there. So that's going to be rule number 2. This next one is going to be rule number 3 and rule number 4. Okay, so first we're going to do a product of powers, and then we're going to do a quotient of powers. So we'll do 10 squared times 10 to the 7th is going to be equal to 10 to the 2 plus 7. And that's going to still be over 10 to the 5th. And I'll erase this in just a second, but just so you can see it. This is going to be equal to 10 to the 9th over 10 to the 5th. And then 10 to the 9th over 10 to the 5th. Because they are like bases, we can now use the quotient of powers rule. So this is now going to be equal to 10 to the 9 minus 5 power, which is going to be equal to 10 to the 4th power. And that's going to be equal to 10,000. Okay. So another way that you can think about it too is if you started and just eliminated by doing 10 to the 7th over 10 to the 5th, you would see that you'd have 10 squared left over in the top, and 10 squared times 10 squared is 10 to the 4th. That's another way that we can visualize it. But let me go ahead and erase this right here, just to avoid it being in the way. Okay. Alright, so this next one looks a little daunting, but it's not too bad. We just have to be really careful here. So what you want to do when you have these expressions here, we can use the rules of, we can't really use number 5 here because it's not a power of product. So these are sums and differences. So the best strategy for these is to go ahead and simplify the parentheses first. So this is going to be 4 to the cube times 4 squared plus 12 squared. Okay. Alright, so now what we are going to do is go ahead and simplify this expression here. This is going to be rule number 3 for this part, because it's going to be a product of powers here. So 4 cubed plus times 4 squared is going to give us 4 to the 3 plus 2 power, which is 4 to the 5th, plus 12 squared. So 4 to the 5th is 1024, and we're going to add that to 12 squared, which is 144. So this is going to be equal to 1024 plus 144, which is going to be equal to, as a final answer, of 1168. Okay, oops. Alright. So this next one here is going to be using what looks like the rule number rule number 6, yeah. So this is going to be in the denominator. You're going to see that there's a power taken to a power. That's going to be rule number 6 here. And then we're going to be also using the quotient rule that you'll see, because we're actually going to end up with like bases. So 12 minus 5 to the 7th power is going to be 7 to the 7th power, and then we're going to divide that by 7 to the 7 squared, but we're going to take that and we're going to put it to the 2nd power. That's going to be equal to 7 to the 7th power over 7 to the 2 times 2 power. And that's going to be equal to 7 to the 7th power, over 7 to the 4th and that's going to then be equal to the quotient of these two like bases. So now we're going to have this equals to 7 to the, again, we're going to subtract the exponents here, so this is going to be 7 minus 4, which is going to be equal to, sorry, I'm going to go off the page a little bit here, be equal to 7 cubed, and 7 cubed is going to be, I believe, it is, so let me check here, okay, 343. Alright, so that's going to be our final answer for that one. So a lot of steps in that one, but again, it's just using some rules here. So we did use rule number 4 as well. Okay. Alrighty. So with our essential question check-in, summarize the rules for multiplying powers with the same base, dividing powers with the same base, raising a product to a power, and raising a power to a power. So when we multiply powers, with the same base, we keep the base the same and add the exponents. For quotients with like bases, we subtract the respective exponents. For a power, or for raising a product to a power, we take each of the individual terms of that product to the respective power, for raising a power to a power, we leave the base the same and multiply the two exponents. Okay. Alright guys, I hope this helps you guys out. I know this one was a little bit more detailed, especially with these expressions down here. But again, these 6 rules really come in handy for starting to see these exponents as part of expressions. And the thing that's interesting about it too is we learned order of operations a little while back, but we never really touched too much with exponents, it seemed. It seems like a lot of the times we were just focusing on that multiplication and division always trumped addition and subtraction, and then parentheses were always the kind of the trump of everything. So again, I hope this helps you guys out. If you have any questions at any time, please don't hesitate to ask. If you have any requests for any certain topics, please don't hesitate to request those either. But thank you guys so much for watching. Please take good care of yourselves, and I hope to see you soon. Bye.